Hello everyone! Site investigation is a process by which the ground conditions on the site and their characteristic parameters are determined. Some key acquirers are topographical and geological maps, records of previous site investigations, current and previous land. These data are also used to plan the direct ground investigation using boreholes. Near surface soils tend to be softer and weaker and more variable than deep soil, and they therefore may require more extensive and more refined methods of site investigation than deep foundations. If the contractor is free to build a returning structure by any method, then, for example, he might place the structure with a minimum of disturbance to existing soil. In the first case, the structure might have to sustain lateral air pressure close to those in situ existing before construction, or more likely, if the wall was allowed to yield away from the soil sufficiently active earth pressure, which would be determined from in situ soil properties. In the other case, he might excavate the soil adjacent to the structure and replace it after construction. Then compaction methods will largely control the final pressure. In this case, the data on the local ground condition will have little value when calculating the earth pressure to be supported by the wall. When the construction method is not defined, it is difficult to argue that any design is either reasonable or possible. We can conclude that these two techniques will lead to completely different pressure distribution and magnitudes between the soil and the structure. The magnitude of earth pressure mobilized on the structure will be related to wall soil placement techniques, wall movement relative to the soil, shear strength developed between the wall and the soil, shear strength of the soil itself, wall, soil, groundwater geometry, and external loads. It is essential that the designer correctly anticipates the wall soil placement techniques to be used, the direction of wall movement relative to the soil, and the probable worst groundwater conditions. Compared with these factors, the choice of soil parameters is less important, provided that those parameters are relevant to the design method and realistic and are relatively conservative. In general, the designer will require knowledge of the geometry of the problem, these including the height and inclination of supported soil surface, geometry of ground surface, distribution of force of soil types in 3 dimensions, position of any external loads, and position of any existing structure to be protected. The bulk density of the soil. This will often be in the range of 1.6 to 2.2 milligram per meter cubes and may well increase with depth. Groundwater conditions. These are required for the worst conceivable condition in the life of the structure. It may be necessary to carry out seepage studies, perhaps using flow net sketching, in order to obtain an estimate of the final groundwater level and pore water pressure variation on the shear surface and the back of the wall. Soft strength parameters. This will vary according to the type of problem. In general, the designer will require the knowledge of the peak effective strength parameters for the soil that the wall is to support, since active earth pressures are nearly always very much greater in the long term than the short term. Soil stiffness parameters. Soil stiffness will be required for analysis of wall and ground displacements, typically carried out using the finite difference or final element computer code, and for foundation settlement predictions. Soil stiffness values can be obtained from in-situ tests, from laboratory tests, or from back analysis of similar structures in similar ground conditions. In-situ horizontal stress profile. When computer analysis involves constitutive soil models based upon both elasticity and plasticity, it will be necessary to have a detailed knowledge of soil stiffness, effective strength parameters, and the initial in-situ horizontal stress. In-situ horizontal stress is both difficult and expensive to measure and can usually only be derived from either self-boring pressurometer test in situ or from suction test on laboratory specimen. The development of earth pressure behind a returning structure is generally extremely complex. Therefore, even sophisticated analytical methods cannot approach the real situation, and all design is in effect semi-empirical or empirical. Soil investigation should at least consist of a depth study and sidewalk over survey, together existing information of the site, probing, boring, or drilling to determine the soil profile and variability of the ground, in-situ testing to obtain data on soil conditions, sampling and laboratory testing for direct determination of the properties of clay soil. Let's see depth studies and sidewalk over survey. Depth studies should include examination of records of previous use of the site, current and old topographical maps, geological maps and memoirs, and finally air photographs when they are available. Previous site investigation reports may be available for nearby site. All this information will be help in giving an idea of probable ground conditions and their variability beneath the site. Depth studies are important because the type of retaining structure to be used will often depend on soil conditions. They are also important because the type of work to be carried out during site investigations will depend on the soil conditions encountered. The two main types of in-situ tests used around the world are the standard penetration test (SPT) and the cone penetration test (CPT). The SPT test is carried out in a borehole and essentially involves counting the number of hammer blows and that are necessary to drive the thick wall tube 300 mm in the ground at the bottom of the hole. Point to note are boreholes disturbance can change the N value if there is a choice of small diameter boreholes or boring methods that do not apply suction to the base of the hole are to be preferred since the extent and amount of loosening are reduced. The hammer used for the SPT varies around the world. Different hammers deliver different energies, and since the N values is inversely proportional to input energy, it is necessary to correct the measured N values to a standard energy level. It has been agreed internationally that this is 60% of the free fall energy of the weight. The N value corrected for hammer energies is denoted N60. In sands and gravels, which are non-corrosive soil, the effective stress at the test level has a significant effect on penetration resistance. The same sand at the same density will have a higher strength and stiffness at depth than it has near the surface, and this will be reflected in the measure of N value. The N value corrected for both overburden, pressure, and hammer energy is denoted N160. Therefore, in clays, the SPT N value obtained in the field must be corrected for energy, whilst in sand and gravel it must be corrected for both energy and vertical effective stress. The SPT N value is increased by soil containing of coarse particles. Since more correlations have been obtained for sands, tests in gravels may give over-optimistic results. The SPT test is far from perfect, but it can be used in almost all soils, and a small sample is obtained for visual description. It is therefore widely adopted in practice, except in soft soil where very low blows count results. In softer and looser soils, the use of CPT is preferable. A 60-degree cone with 10 cm square face area is pushed into the ground at the rate of 2 cm per second. The force necessary to advance the cone is measured. At 150 cm square friction sleeve is typically fitted behind the cone and measures shear stress between the soil and the cone at this location. A pore pressure sensor may also be used, and it's typically fitted between the cone and the friction sleeve. The force applied to the cone as it is pushed into the ground may be measured mechanically or electrically. Wherever possible, an electric cone should be used. The cone resistance is calculated by dividing the force necessary to advance the cone by its 10 cm square cross-sectional area. The sleeve friction is calculated by dividing the vertical shear force on the friction sleeve by its 150 cm square surface area. The friction ratio is obtained by dividing sleeve friction by cone resistance. Typically, near continuous plots of QC and IF are produced as a function of depth. The CPT has many advantages over the SPT. No boreholes is required, so borehole disturbance is avoided. The process is more or less automated, so operator independence is achieved. Because data are taken electronically using strain gauge sensor, very frequent readings can be obtained, allowing the ground profile to be examined in detail. There are one or two important disadvantages. However, the equipment cannot always penetrate the ground to the depth envisaged, as obstructions such as dense gravel, cobbles, and boulders can cause refusal. No sample is obtained for visual description. The common methods of sampling and in-situ testing used during boring drilling are described. Film to very stiff clay. Thick wall driving on the step 100 mm diameter open drive tube samples are typically taken at 1 to 1.5 meter centers down the hole. Small disturbed samples are taken between undisturbed samples. Very soft to film clays or peat. Thin water piston drive samples may be taken at 1 cm and 1 meter, or if laboratory tests are required, or alternatively in-situ vein tests can be carried out to obtain undrained shear strength. Sand and gravels. Standard penetration tests (SPT) are carried out at 1 to 1.5 meters centers. Small disturbed samples are recovered from SPT split spoon in sand. In sands and gravels, large disturbed samples are taken at 1 meter centers between SPT tests. Rock. Continuous rotary core is taken with the aim of determining whether rock head or boulder have been encountered during soft ground boring. Also, small disturbance samples should be taken immediately when a new soil type is encountered. 3 groups of borehole may be used. The main boring at 50 meter center along the center line of the wall are taken to twice the proposed wall height below the upper level or to a known geological stratum. The first phase intermediate borings are carried out after the completion of the main borings on the active and passive side, again at 50 meters centers along the proposed wall position. If the ground proved to be very variable, a second phase of intermediate boring is carried out with a boring depth dictated by the findings of the previous boreholes. This amount of investigation will be rare in some countries. Rather than carry out large number of boreholes, it may be better to extend the information gained from main borings by carrying out static cone penetration tests or continuous dynamic probing on either side of the center line, since these will be cheaper and faster to carry out. Both these types of tests are carried out without a borehole, and so it is necessary to have some borings to identify the soil types on the site. The objectives of site investigation, drilling and testing are threefold: to divide the subsoil into simplified soil type or groups, soil grouping and the assessment of the soil variability within each group is normally carried out on the basis of visual sample description, moisture content, attribute limits test, and particle size distribution. These last three types of tests are often referred to classification tests because they are used to classify the soil into groups of materials which are expected to have similar behavior. Visual sample description is extremely good technique for soil grouping, but it must be carried out by a trained and experienced geotechnical engineer. A large number of classification tests should be carried out if the true variability of the soil is to be determined. To determine the variability of each soil types or groups, and in addition, the results in the in-situ tests such as SPT or in-situ van test are very useful for assessing variability. Even better, however, are tests which give a more or less continuous record with depth, such as static cone test or the continuous dynamic penetration test. To obtain parameter representative of each group for design purpose, all of these activities are normally carried out. In clays, it is possible to take samples that are reasonably undisturbed and can therefore be used in laboratory tests to determine parameters for retaining wall design. However, it is important to bear in mind that the boring and sampling process produce soil disturbance which change the properties of the material to be tested. A full description of the cause and effect of soil disturbance can be noticed. It is sufficient to note that the amount of soil displaced by a sampling tube affects the degree of sample disturbance. Thin wall tubes are better than thick wall tubes, for example, displacing 3% to 45% of the sample area. It often proves impossible to recover samples of soft clay when using a thick wall sampler. The detailed cutting shoe geometry also affects disturbance. Sharp cutting shoes are better than blunt ones. The method advancing a sample tube has an effect on disturbance. Push tubes are better than driven tubes. Block samples hand cut from pits tend to be less disturbed because disturbance caused by the boring rig is avoided. However, it is difficult to take block samples at depth in soft clay or below the water table. Sample and test also need to be representative of the ground from which they are taken. This means that they must be large enough to contain all particle size present in the ground, plane of weakness such as fissure, drain features such as sealed covered fissure, lamination or lenses of sand. In addition, They must not be damaged during transportation to the laboratory, and they must not be allowed to dry out during storage. All samples should be carefully sealed as soon as they are brought to the surface to prevent moisture loss. Laboratory testing for strength properties is usually carried out in the triaxial test. Tests can be carried out either drain, where a drainage vent is left open to a fixed water pressure during shear, which must be carried out slowly enough to allow excess pore pressure set up by gyratory stress increase to drain. On drain with pore water pressure measurement, where specimen drainage is prevented and the pore pressure in the specimen is measured during shear using a pore pressure transducer. On drain, where the vent is closed during shear, pore pressure is not measured and the test is interpreted in terms of total stress. Drain tests and on-drain tests with pore water pressure are known as effective stress triaxial tests and are routinely used to measure the effective strength parameters C' and Phi' of clays. The third type of test is used to determine the on-drain shear strength of the soil, which is useful for design of structures for short-term conditions. Another form of laboratory test that may be useful is carried out in the oedometer test. Here, a disc of scale is confined laterally by a metal ring which being compressed under increasing vertical stress. The results are plotted either as vertical strain as a function of logarithm of applied vertical stress or volume ratio, or specific volume as a function of logarithm of applied vertical stress. The vertical stress is typically doubled at each loading stage, and there may be unloading as well as loading stages. The rate of compression under each load is interpreted in terms of coefficient of consolidation CV, which can be used to estimate the speed at which consolidation of foundation, for example, might occur. For soft clay, the test is routinely used to estimate pre-consolidation pressure and the compressibility index. And small specimen height means that bedding effects will lead to very significant underestimate of stiffness of stiff and very stiff clays. The loads on earth retaining structures are very significantly influenced by groundwater condition. Therefore, it is essential that ground investigation of earth retaining structures should look into as full as possible the regimes of the groundwater and its waterfront structures, the season and tidal variations of water in front of the wall. Groundwater may exist in a number of forms. Hydrostatic conditions. Here, the pressure of pore water within the ground increases linearly with depth, such that any distance below the groundwater table. This means that there is no vertical component of seepage. Artesian groundwater. Groundwater is impermeable aquifer confined below a relative impermeable material such as clay, which exists at a pressure higher than that due to its distance below the top of the aquifer. When a hole is drilled into the aquifer, groundwater rises up the borehole through the relative impermeable material and may rise above groundwater level. Perched groundwater. Rainfall seeping from ground surface through relatively permeable soil rests on top of a less permeable layer, below which a more permeable soil exists. When buried through this ground, a water stride will occur at or above the level of impermeable soil, but the groundwater will drain down the hole once the lower, more permeable material is reached. In developing countries, this situation will sometimes be found in cities where the water level may be untreated effluent. Under drainage. This is the reverse of artesian condition and has occurred in many areas of heavy populations. as a result of exploitation of aquifer for domestic or industrial water supply. The deeper a case borehole extends in the clay, the lower will the equilibrium water level within it. The form of groundwater is important not only for the design of the permanent works, it has very serious implications for construction costs because of its influence on the difficulty of carrying out groundwater works. In this respect, it's important to know some details, not only the geometry of subsoil and the forms of groundwater regime, but also the permeability of each soil types. Thank you, and let's see the next time. Subscribe to be notified for the next video. Thank you.